My name is Olga Palazhcenko. I'm an associate professor in chemical engineering. I'm also a member of the Center for Nuclear Energy Research here at UNB and the director of the Clean Create program. We need more energy. So whether that is for electrification, whether that is for AI data centers, maybe that's to support, growing energy needs in a whole variety of sectors. So you're looking at electrification of roadways, you're looking at building more of everything, right? More hospitals, more people, more infrastructure. We fundamentally need energy. It's a very real prospect that we're going to eventually run out of clean water. Like, we're going to have to draw from sources such as salt water. The chemical processing that's needed to remove the chlorides, the bromides, all of those ions to actually have either really pure research grade type 2, type 3 water, or even clean drinking water, that is all energy intensive. That requires a lot of heat, that requires a lot of electricity. So even if we're kind of looking outside the immediate electrification of the grid and all of that, there are all these other sectors. And even through electrification, we're looking at electric vehicles, we're looking at smart grid. So the demand for energy and electricity, everywhere we can get it, we'll take it. And SMRs just give us a more convenient way. The smaller you go, we're talking about micro reactors and nano reactors, the more that you can put a reactor on the back of a 18-wheeler and you can move it somewhere. So move it to where you do have a very secure AI data center, or move it to somewhere that you need to build a water purification, desalination plant. It is a tremendous capability. So if these advanced reactors, which now we're referring to even as nuclear batteries, right? Because you can pick them up, you can put them somewhere, and you are basically producing your energy right there on the spot. The more kind of advanced reactors are new to us in Canada, there's still a lot of work to be done there in terms of the materials of construction and kind of the performance of all of these materials in all kinds of conditions. A lot of the fuel types and cladding types have already been used in either research reactors or test reactors. That usually is being outside of Canada, so it's being in places like France or the US. So if we're really looking to take these kind of established at the kind of research scale materials and fuels and move them to commercial, we're going to need to do a little bit more kind of testing and fill in some of those gaps. So basically, as you are splitting your atom, so that is usually uranium-235, as you are releasing that heat, when you split that atom, you also form what we call fission products. So it's usually two pieces. You've split your atom into two smaller atoms. One's a little bit bigger, one's a little bit smaller. Some of those fission products can basically move or diffuse to the surface of where the cladding, so the outer casing here, it would just be on the inside of that. And then after kind of prolonged at high temperatures being stuck together, you can have a little bit of migration of some of the chemicals that make up whatever the cladding is. You're basically pulling out very slowly some of the elements that make up that outer casing. We're very interested in seeing how long-term, once you've taken that fuel out and that interaction has happened and you are basically de-alloying or pulling elements out of that cladding, has that weakened the cladding? Has it weakened it structurally? So is it easier for cracking or stresses to happen to it? Is it easier for regular corrosion, basically chemical reactivity with water to happen? Realistically, those type of tests are 5 to 10 or more years. We're definitely looking at a shorter scale, so we're looking to accelerate some of that damage and do basically more stuff to the cladding that would cause a more likely corrosion or perforation reaction. We will continue to have more energy needs, and whether it's an SMR or it's a traditional larger scale reactor, we will continue with nuclear power in the province, because without it, we would fundamentally not be able to really power much of what we currently have for energy demand, much less the demand we're going to need by 2050. So supporting research at kind of an academia level really all feeds into that ability of the industry and the decision makers and the policy makers to keep that momentum going, to have the information they need to make those decisions, to build those reactors. So it really all becomes one cyclic chain of, we need funding from the decision and the policy makers, but they need the information from us to be able to make better informed policy and decisions. So it really is all an interconnected web, at least in engineering. The dream to do applied research. I love doing fundamental research, and I love finding answers to questions that kind of just support knowledge, but to have research that directly affects either policy or decision making, or, for nuclear, it's the pathway to licensing. If that leads to, industry doing design changes or kind of developing their technology further, that's great. But more fundamentally, it's not that we're looking to, make huge changes to how the industry is kind of doing their own R&D on this. It's really to provide a better understanding to the regulator, to the general public, to really all of our stakeholders. So if they do have existing questions on how does this material perform at this much higher temperature, what happens if there's some kind of worst case scenario, if they can go to the open literature and find information on that without having to do, their own independent research and to hire their own consultants, if we in academia can sort of backfill that knowledge so that it's readily available when they are looking to do licensing, vendor reviews, and all of these kind of processes on the road to commercializing these technologies, then to us, that's a job well done.